Yes, we can see it.
Okay, perfect. So it's 6:30. I think we can start. So welcome to this session on Nexa solution in 4 and higher dimensions. So this is the I think almost the last day of this nice meeting, and today we have this list of speakers. So I hope you can finish your talking time, so you can all of the other speakers to finish their talk as well. So the first speaker is Gonzalo Olmo from University of Valencia, and he will talk about multi-center and rotating solutions in Eddington-inspired boring field gravity. So I will stop sharing my screen. So please, Gonzalo, could you share your screen? So I will also ask Jose to mute his microphone, please.
Thanks.
Okay, so please go ahead.
Thank you, Fabio. Okay, so I'm going to present some exact solutions, and I will discuss also the physical interpretation that represent rotating objects and multi-center solutions without any symmetry in a particular model of metric affine theories of gravity. And this is the Borning-Feld gravity model, or also known as Eddington-inspired Borning-Feld, EIBI. So we are considering modified gravity, and the reasons for this in general are well known. Okay, we have important open questions, and we want to solve them and have a different perspective on them beyond general relativity. So it's nice to explore strong gravity effects like the early universe or compact objects, or understand some problems, observational problems, mainly with the cosmology at larger scales, and also the compatibility between gravity and quantum theory is not clear from the perspective of general relativity. So some aspects like singularities or simply the compatibility with quantum phenomena of particle creation, it's interesting to explore it from other perspectives, and modified gravity offers a possibility. So from this modified gravity perspective, so we have more freedom because we have different field equations, but this freedom has a price to pay. So it's the fact that finding new exact solutions is difficult in general, and also numerical solutions. We have different equations, numerical problems are not easy to solve. And so spending time developing new methods is always expensive. So it is not, let's say, as straightforward as in general relativity, which is not easy either, but going beyond is even more difficult. And in particular, finding exact solutions is very important because they allow for many different theoretical considerations and allow to have analytical control on some parameters and limits, which is always very useful. And also being able to treat numerically the equations is crucial in order to confront theories with observations. In particular, if you consider the collision of two black holes to generate gravitational wave profiles, this is a problem that we can't handle in general relativity. But beyond that, it's really a very expensive issue. So among the many different gravity theories that are in the market nowadays, I'm going to focus on a particular model in a particular family of gravity theories. Okay, so this family is what we call Ricci-based gravity theories, and I will give technical details of them later. Now let me advance some aspects. And the point is that these theories allow, provide a very useful scenario to explore new gravitational phenomenology, mainly because we can find exact and numerical solutions. So as many exact and numerical solutions as in general relativity at least. Okay. And this is so because any solution of general relativity can be used as a seed to generate new solutions in this family of theories, not just in the model I'm going to present, but in the whole family. Okay. So we have, in the last year, we have studied boson stars numerically using this relation between GR and Ricci-based gravity theories, also rotating solutions and multi-center configurations. So this means that you don't need special configurations. Boson stars typically are spherically symmetric, rotating objects are axially symmetric, but multi-center configurations do not have any symmetry. So anything you can do in general relativity can be done in these theories. So now let me enter into some technical details, in particular to explain how Ricci-based gravities are seen as metric affine theories. So the first thing is to consider the action principle. So the action of these theories, as I said, they are called Ricci-based because the key object in the gravity Lagrangian is the Ricci tensor, in particular the symmetrized Ricci tensor. So the Lagrangian is constructed as a scalar function of traces of this quantity, okay, the contraction of the symmetric Ricci tensor with the inverse metric. And the matter action is just written as in general relativity, simply asymmetric theories of gravity, in fact. So following the equivalence principle, we have the matter fields here in red and the metric. So the connection, which is used to define the Ricci tensor and is a priori independent of the metric, is not does not appear in the matter action. This is just a choice. One could make generalizations, but in principle, just to be on the safe side, as far as experiments are concerned, we follow the prescription of the equivalence principle and just keep the metric on this side. Okay. So the field equations of these metric affine theories can be found by independent variations with respect to metric and connection. And the details are in many papers, but in particular in this one, okay? Because this one derives the complete field equations, considering torsion and non-metricity, the role of projective invariance is related and used, in fact, this symmetry is exploited to find the general formal solution, including torsion. And this explains why we are considering only the symmetric part of the Ricci, okay? Because in that case, we have a projective invariance, and this symmetry allows to trivialize torsion, okay? So torsion is not really very important unless you consider fermions, okay? So for any other matter source without fermions, torsion is really a gauge degree of freedom and can be gauged that way. And for a discussion of instabilities in these theories and beyond, in the general case, not without the restriction to the symmetric case, you can see this paper by José Beltrán and Adrià Delon. It's very complete and nice. So the important thing is that in metric affine theories, the field equations are typically second order, but it is not a guarantee that the theory is free of instabilities. But if you consider the symmetric case, so when the theory is projectively invariant, then ghost-like instabilities are not present. So these theories are safe from that part. So an important aspect of these theories is that the connection can be solved exactly. As I said, there is a symmetric part, which is given by the Levi-Civita connection of an object H, which can be seen as an auxiliary metric. And this auxiliary metric is related to the metric that couples to the matter fields, we can say the physical metric, by this object omega, which is what we call a deformation matrix. Okay, so this object depends on the particular gravity Lagrangian, so it is model dependent, but there is a general parametrization for the connection in terms of this object and this deformation matrix omega. The deformation matrix only depends on the stress energy tensor of the matter fields. Okay. So once you have a particular gravity and matter model, you have a specific matrix omega. Okay. So, and this describes the symmetric part of the connection. And as I said, the antisymmetric part, the torsion, is generic and is really irrelevant because can be eliminated by a projective choice, okay, a particular gauge in the projective family. So, and this is for the metric and for the connection. And using this metric H, the metric field equations can be written in compact form like this. Okay. So on the left-hand side, we have the Einstein tensor for H, and on the right, we have the stress energy tensor, its trace, and then the determinant of omega, but remember that the determinant of omega is a function of the matter, and the gravity Lagrangian. But the gravity Lagrangian is a function of the Ricci, and as we can see here, the Ricci is a function of the matter sources. So this function, this LG, can also be written as a function of the matter. So everything on the right-hand side is a function, a nonlinear function of the stress energy tensor. Okay, so in some sense, this works like general relativity, geometry on the left-hand side and matter fields on the right-hand side. Okay, but there is a small problem, which is actually becomes a big problem, and is the fact that on the left we have the metric H, but on the right we have G. Okay, and G is related to H in a nonlinear way. Okay, because this omega depends on T mu depends on G, and so this is in general a very complicated nonlinear. Okay, but we can still work with that. Now let me give a couple of examples to illustrate what this omega is. Okay, because the new thing in these theories is this deformation matrix. So let me give a couple of examples. For instance, if we consider the gravity Lagrangian to be this quadratic f of r model, the Starobinsky model, then one finds from the field equations that the omega is diagonal. So it is the relation between the metrics H and G is conformal. Okay. And this conformal factor, using the field equations, is just a function of the trace of the energy momentum tensor of the matter. Okay, so this function f of r can be written as a function of t, and the general equation is this one. Now, if we consider the Born-Infeld gravity model, which is the one we are interested today, the gravity Lagrangian takes this form, and the matrix omega can be obtained by solving this equation. Okay, the determinant, the square root of the determinant, the inverse of the metric of the matrix omega, and on the right-hand side we have this lambda, which is just a constant. You can set lambda to 1, and then the stress energy tensor. Okay, so by solving this matrix equation, we just get the form of omega, and we can work. Okay. So now let me explain the crucial relation that exists in Ricci-based gravity theories with general relativity that makes them specimen. The point is that we can find a correspondence between the space of solutions of general relativity and the space of solutions of Ricci-based theories of gravity. And this is so because if we are given a particular gravity Lagrangian and a matter Lagrangian, then we can transform this problem into general relativity coupled to a different matter Lagrangian. Okay, so if we have modified gravity with standard matter, then we can map this problem into a standard gravity with modified matter. Okay, so this is the key problem, or the key advantage of these theories. So, and explicit examples of how to do this appear in this series of works, and in which we consider specific couplings to scalar fields or to anisotropic fluids, nonlinear theories of electrodynamics, or in general electromagnetic fields. Okay, so this is in a sense, this can be interpreted as the fact that modified gravity can be studied without modified gravity. This is modified gravity, this thing can be studied from within general relativity itself. You just simply need to modify the matter sector. Okay. So how this this mapping between modified gravity and general relativity is constructed is formally expressed through these relations. Okay. So essentially, see if on the left-hand side we have general relativity, so this function of the matter sources can be written or can be reinterpreted in terms of a modified stress energy tensor. So doing the same with the field equations, we can find the correspondence and that's it. So after a long calculation, you can get that. And for instance, if we consider Born-Infeld gravity with a scalar matter, taking, for instance, in general relativity, if we consider general relativity with canonical matter, this Lagrangian, then we can transform this combination into Born-Infeld plus modified matter, and the modified matter takes this form. Okay, so if we start in GR with this Lagrangian, the corresponding theory, matter Lagrangian in Born-Infeld gravity is this one. Okay, and as you can see, it has the square root structure of Born-Infeld theories. Okay, so somehow the nonlinearity is also transferred to the.
Sorry, Gonzalo, you have 10 minutes left that you can decide. It should be 5 minutes plus 5 questions, but you decide if you want to exceed, you just leave a few minutes for questions.
Thank you. So we did that for a scalar matter sector, but we can also play with anisotropic fluids. So this is the fluid coupled to the Ricci-based theory. This is the fluid that we propose for the general relativity sector. And the important thing is that the metric for the Born-Infeld theory can be written in this way in terms of the general relativity variables. So this would be the solution for a theory, for a matter sector in general relativity, and this is the matter sector in general relativity. So whenever you have the solution, you can get in GR, you can get the solution in Born-Infeld gravity. Okay, and this is what we did to obtain exact solutions in Born-Infeld gravity. Essentially, we interpreted the Kerr-Newman metric in GR as an isotropic fluid and use that to generate the solution in Born-Infeld gravity. The details are in this paper, but the sketch of the construction is here. So you take the Kerr-Newman solution. Actually, we have here. If you take the Kerr-Newman solution in general relativity and interpret it as an isotropic fluid, then to do this interpretation, you just take the line element of Kerr-Newman and compute the Einstein tensor. So this represents the left-hand side. And then you use an isotropic fluid in general relativity to write the stress energy tensor of that fluid. And then you compare the left-hand side with the right-hand side. Okay, so the energy density in particular, this rho h here is this rho q. Okay, so by direct comparison, you already have this energy density. For electromagnetic fields, the radial pressure is minus the energy density, so this is already known, and then the orthogonal pressure can be obtained, and also the angular frequency can be obtained from this comparison. So these functions f1, 2, and 3 are complicated functions of the variables, but it's just an algebraic problem. And then you find these relations. Okay, so the Kerr-Newman solution can be interpreted as a solution for a fluid, and with that, we just use the formula to obtain the line element for Kerr-Newman in Born-Infeld theory. And there is the interpretation of these fluids can be done in terms of electromagnetic fields, and you find that since the Kerr-Newman is the result of coupling general relativity to Maxwell electromagnetism, This line element here is the result of coupling Born-Infeld gravity to Born-Infeld electromagnetism. Okay, so this is really a very nice interpretation. And well, once you have this line element, you can extract all the physics. For that, please go to the paper because there are many details. In particular, you need to explore first the non-rotating solution because there are new horizons, new properties. And then once you have an idea of what happens, then you go to the rotating case. The most relevant point I would mention is the fact that depending on the sign of epsilon, you have two different configurations. If epsilon is positive, you have a standard black holes, but if epsilon is negative, you find wormholes. So this line element for negative epsilon represents a rotating wormhole. Okay, this is similar to what Renan Magallanes found for quadratic gravity on Wednesday. Okay, so these wormholes persist also in the Born-Infeld theory with rotation. And a similar approach can be used to find multi-center solutions, but instead of using the analogy with fluids, we can, or it is convenient to use the complete electromagnetic correspondence, which is given by this expression. Okay, you have a matter electromagnetic Lagrangian determined in terms or defined in terms of these electromagnetic invariants. Okay, so the relation between the solution of GR and the solution in Born-Infeld gravity is given by this expression. Okay, so if this is the solution of GR with this U being a multi-center function, a harmonic function that satisfies these equations with many centers, each xi represents a center, and this is the mass of the center, then this solution in GR generates this other solution in Born-Infeld gravity. Okay, and again, the case with epsilon negative represents multi-wormhole solutions, and the details of these solutions are very complicated because there are many different cases. Everything is explained in the paper that must be cited somewhere here. Yes, it's here, this paper. You can click on the link. And well, as I said, we have multi-wormhole scenarios, but they are not completely satisfactory because there are some curvature divergences at the wormhole throat. But anyway, this does not prevent the possibility of extending geodesics. So even if there are curvature divergences, we have geodesically complete spacetime, and therefore they are non-singular. And well, you can also use the previous results to set some strong bounds or experimental bounds on the parameters of the Born-Infeld theory, but I don't want to waste all the time here. So the conclusion is that in the last years, there was an important breakthrough in these theories, in Ricci-based theories. So we found that the modified dynamics of these theories can be analyzed from within general relativity itself. So we are exploiting this to generate many new solutions, exact and numerical, and with and without symmetries, those solutions. So in the future, we want to study the dynamical scenarios using numerical methods to extract information on gravitational waves and generate a catalog of exotic compact objects and to explore and interpret their features. And that's all. Thank you. I think we have time for 2 questions.
Thank you, Gonzalo, for this nice talk. So are there any questions? Well, if not, I have a couple of questions. Mm-hmm. The first is whether this model can solve singularity problem of general relativity, as you mentioned that you have geodesically complete spacetime. And the other question is about cosmology. What can you say about cosmology?
Well, this particular model, the Born-Infeld model, performs very well in cosmology because this was actually one of the first solutions that was found because they produce bouncing solutions. Okay. Well, there are 2 kinds of solutions in cosmology. If epsilon is negative, you have bouncing solutions, but if it is positive, you have asymptotically Minkowskian solutions. So you have two ways to get rid of the singularity. So it was a success in cosmology, and so many people started to work on that. And then we explored black holes, and if epsilon is positive, you don't get singularity resolution. But if epsilon is negative, generically you get singularity resolution, even if you have curvature divergences. So geodesics are complete, and wave propagation is also well behaved in this scenario. So generically, the model performs very well.
Okay, so choosing properly this parameter, you can avoid any singularity.
Exactly.
Sounds good. So I think we have finished. So thank you very much, Gonzalo, for your talk. So let's continue with the next speaker. It is Robert Zwark from Charles University, who will talk about Kunst spacetimes in the Einstein gas-bounding theory. So please unmute yourself and.
Okay, I hope you can hear me and you can see me.
Yes, maybe you can put full screen mode.
Exactly. Okay, so I hope that it works. Okay, so
yeah, okay. Thank you.
Thank you for the opportunity to speak here, and I will talk about Kunst spacetimes in the Einstein-Gauss-Bonnet theory. So it's natural to start with some review about this theory. It's the simplest representative of so-called Lovelock theories. It means that you would like to preserve the second-order field equations and Bianchi identities. And in this sense, Einstein's GR is unique in 4 dimensions, but it can be extended when you allow, say, dimension as a free parameter. So the first non-trivial correction to the famous Einstein-Hilbert action is so-called Gauss-Bonnet term, which is just a topological term in 4D, but became non-trivial in higher dimensions. There are various scenarios where this theory is important or can appear, for example, as a low energy limit of some heterotic string theories. I would like to confess that I'm not expert in this theory, but I'm interested in exact solutions, especially in GR, but I also would like to see how GR is privileged or unique. And this is a nice playground to see exactly this behavior in the case of say geometries defined by some universal properties. I mean the Kundt geometries, as we will see. So the most natural way how to formulate this theory is in terms of the action. So we have action written here, Einstein-Hilbert part and Gauss-Bonnet correction. Lambda, kappa, and gamma are constants. Gamma equal to 0 corresponds to GR. It means this term is vanishing. D is dimension. For us, it will be a free parameter, typically greater or equal to 5. And variation of this action leads to the field equations. Here it's written in the form that we have the classical Einstein part and Gauss-Bonnet correction proportional to constant k, which is just a combination of kappa and gamma. This Gauss-Bonnet part is written here. There is explicitly the Gauss-Bonnet term and some contractions of the carriage tensors, of the Riemann tensor with Ricci tensor, and so on. And our aim is to derive the second-order field equations. Second order is by definition of the Gauss-Bonnet theory for the Kunst spacetimes. I will tell in a minute what the Kunst spacetimes are, and compare properties of this solution with those of GR, because Kunst spacetimes, you probably know PP waves are the very important solutions in GR I would say. Okay, so we would like to find exact solutions. Typically, in every theory, you have to start with some simplifying assumptions. For example, it's symmetries. You would like to find, I don't know, a spherical symmetric solution, or with some algebraic properties of curvature tensor, of the Wild tensor, some specific algebraic type, or you can start with specific properties of geodesics. And it's exactly our case, because we would like to study spacetimes which admit non-twisting, shear-free, and non-expanding null geodesic congruence. It means that we take some null geodesic vector field, and we can study the transverse behavior within this congruence. And this can be characterized by so-called optical scalars. Again, it's a textbook example. And we have twist, shear, and expansion. It's given in terms of this null vector field. And we assume that all these scalars are vanishing. What does it mean for the spacetime, for the spacetime metric? So it's written here. The probably crucial condition is that our congruence is twist-free, which is equivalent to the existence of null foliation, where the null vector field of this congruence is normal or tangent, because it's null vector field, to the null surfaces of this foliation. And it very naturally introduces coordinates on this manifold. And you can also start with, say, intuitive construction of these coordinates, starting with some trajectory in your space-time with arbitrary coordinates. And this trajectory is parameterized by some parameter u. And in every instant along this trajectory, you can construct null hypersurface, which will be labeled by u equal to constant. And then you take some null vector field along this null hypersurface. It will be exactly this non-twisting vector field k. And as another coordinate, you can take an affine parameter along this null vector field. It will be coordinate r. So now we have two coordinates, u and r. And fixing u and r equal to constant, it means that you are somewhere on the specific null hypersurface. You will deal with d minus 2-dimensional space, Riemannian space, and there you can introduce some d minus 2-dimensional metric g pq. So these are our coordinates, which we will use in the next of in the rest of the talk. And the metric of non-twisting spacetimes can be written in this form. So it's adapted to the null foliation generated by affinely parameterized null geodesic vector field. Okay, so we have also shear-free condition, and it tells you that the spatial part of the metric, this d minus 2-dimensional, it's indicated by this circle here, can depend on the affine parameter along the null congruence only via conformal factor, which is written here. And moreover, this dependence is exactly given by expansion. So for a non-expanding geometries, you will end up with R-independent metric of this transverse d minus 2-dimensional space. And it exactly corresponds to the Kuhn class. And here I have a small intermezzo. I would like to illustrate that Kuhn spacetimes are really important in GR. Probably all of you know PP waves, defined as spacetime admitting covariantly constant null vector field. So obviously all the optical scalars are vanishing, and the metric corresponds to the metric I have written in the previous slide. In the Kuhn class, there are also VSI spacetimes with vanishing scalar invariance, direct product spacetimes, or so-called gyrotons, where these off-diagonal terms play an important role in coding some rotating character of the source. And I mentioned in here because I won't be interested in these off-diagonal terms in the rest of the talk, so we can skip it. Okay, so we have an exercise. We have a most general Kuhn metric. We assume that these gyrotonic terms related with some specific matter fields will be vanishing. So because in fact we are only in the vacuum theory, so our metric NZ is written here, and we have two unspecified metric functions, or in fact this transverse metric of d minus 2-dimensional space and this function GUU. Okay, so now we have to employ the Einstein-Gauss-Bonnet field equations, and we can rewrite them in this form using their trace. This HAB, as I said, it's a Gauss-Bonnet contribution, and this H without indices, it is its trace. And if you explicitly evaluate these equations for component RR and RP, where P is standing for the coordinates of this transverse space, you'll find that these two equations are identically satisfied, and then there remain only 4 equations written here. So now we have to discuss explicit form of these equations to obtain solution which we want. Okay, so we can start from the RU component, which seems to be the simplest one of these 4 remaining equations, and it connects geometry of the transverse space, d minus 2-dimensional, with the theory constants. So this constraint is written here, and as you can see, for k equal to 0, corresponding to the general relativity, this equation would imply that scalar curvature has to be constant, and it will correspond to the cosmological constant. In the case of Gauss-Bonnet theory, it's no more true, and scalar curvature of the transverse space, it's indicated by this index S that we are dealing with the metric GPQ and with the transverse space, and this is coupled with the Gauss-Bonnet term. So this is a first difference between GR and Einstein-Gauss-Bonnet theory. We can continue with, say, PQ component or components of the field equations. And again, this is the fully explicit form for our metric ansatz. And we can see that there are curvature terms constructed of the transverse space metric, from transverse space metric. And there is also RR, a derivative of the GU metric function. It means it restricts how this GU function can vary along null geodesic congruence. And it's proportional to this tensorial quantity QPQ. And it's fundamental for our further discussion because it's written here as you can see in GR, it's just metric tensor of the transverse space, but which is in general non-degenerate. But in the case of Gauss-Bonnet theory, there is this Gauss-Bonnet contribution, and it can be combined with this metric tensor, and we have to distinguish various cases, whether it's 0 or not, or its trace is 0. So it's written here. So if you would like to integrate this equation, you can evaluate its trace with trace of this u pq, which is written here. And then you can simply twice integrate gu with respect to r, and you will obtain some quadratic expression in r, but only in the case when q is non-vanishing. Okay, so discussion has to be splitted. And now I only would like to list UP component, which we can see that it restricts some coefficient in GU metric function and couples this coefficient with U dependence of the transfer space metric. It means U dependence characterizes on which null surface we are. Only notation, this symbol stands for covariant derivative with respect to this transverse space metric, and this is UU component of the field equations, and it restricts spatial dependence of GU metric function. And again, we can see that these constraints are contracted with this UPQ quantity, which defines our subclasses. Okay, so we can start with the generic.
Robert, you have 10 minutes, including questions.
Okay, thank you. And this generic case, it means that Q is non-vanishing, its trace is non-vanishing, and therefore also tensor quantity is non-vanishing, and we can simply integrate R dependence of GU metric function, specify the leading coefficient of the quadratic term. PQ equation then gives other constraint for the transfer space geometry. UP component gives a spatial dependence of this linear coefficient in the GU function, and UU component, as I said, restrict spatial dependence of the remaining coefficients in GU. Classically in GR, it corresponds to the amplitudes of Coulomb gravitational waves. Okay, then there is a peculiar case when trace is vanishing and PQ is non-vanishing. This case is not allowed in the Einstein theory because Ricci scalar curvature is given in this form, and as you can see, for k equal to 0, which corresponds to GR, it would be vanishing. Then we have coupling with the cosmological constant, and combining these conditions gives coupling between cosmological constant and the theory parameters. One can discuss that k and lambda is to have opposite sides and cannot be 0, and so on. And then you have to discuss all PQ components of the field equation separately, and you can see that this GUU metric function has to be also quadratic in R, but it's not important now. And there is the third case when this PQ will be vanishing. So there will be special coupling between the Ricci tensor and metric. In fact, we will deal with the Einstein space, or the transverse space will be Einstein space. Again, this class is characterized by specific coupling between the theory constants. Again, it's not allowed in the Einstein theory, and the remaining equations give primarily restrictions for the transverse space geometry. What's interesting, and for me quite surprising, that the metric function GUU, which can be, as I've already mentioned, interpreted, or this function encodes behavior of Coulomb gravitational waves, is fully arbitrary in this case. Okay, I have a remark here that you can see that for U-independent transverse space metric, these two equations are trivially satisfied because here we have U derivatives. And so what remains are only restrictions for the transverse space to be Einstein with some specific properties. Okay, what we have done, because we would like to discuss, or we have discussed geodesic deviation, and the natural way how to express geodesic deviation is to decompose the curvature in terms of the Weyl tensor. So the natural step away was to discuss the algebraic structure of the Weyl tensor. So one can take, say, natural null frame and then discuss possible vanishing of various boost weights what is necessary is to define decomposition or components of the Weyl tensor with respect to this null frame. It's written here. What can be observed for the Kundt metric ansatz, which we have, is that these geometries are of algebraic type at least 2D. It means that the two highest boost weights are vanishing, and moreover, also one component of the boost weight 0 is vanishing, so it corresponds to the subtype D. And in the Einstein-Gauss Bonnet theory, it means employing the restrictions of this theory, we can find that in the generic case, this type will be also 2D, and it will be unchanged without some additional constraints or conditions. In this peculiar case, when the trace is vanishing and tensorial quantity is non-vanishing, we deal with subtype 2AD because we have the Einstein space there, and or this coefficient B is given in some specific form. And in this in the third case, in general, it's again type 2 because both lowest and highest boost weights, psi 2 and psi 4, contain this arbitrary metric function GUU, which is in this case unspecified. So we will again deal with type 2. This classification was done also for the Ricci tensor, but again, it's not important here. So the last point I would like to mention is some explicit example, and it's geometry where we, in addition, assume that this D-2 dimensional transverse space is of a constant curvature. So the Riemann tensor can be written in terms of this transverse space metric in this form, and the transverse space metric is conformally flat with this conformal factor here. RU component of the field equations, as I said, it's some coupling between transverse space geometry, immediately gives condition for the scalar curvature of this transverse space. And as you can see, there are two branches of solutions because there is some square root, and the plus branch has GR limit. You can simply expand the square root and you can see. And the minus, it's just a case in the Gauss Bonnet theory, which is no GR limit. And QPQ is non-vanishing here, and you can discuss all the remaining field equations. You can see that some of them are trivially satisfied, and that this coefficient near quadratic terms in GUU metric function is given here. It's given just by or determined by the scalar curvature of the transverse space. Coefficient near the linear term is independent of spatial coordinates, and this last coefficient or function here in GU term is restricted by the Laplace equation, and it encodes, say, amplitudes of gravitational waves. It is connected to the interpretation of this solution. So algebraic type is 2 BCD, so there is only, say, one non-trivial boost weight 0 component of the wild tensor, and it can be interpreted as type 2 gravitational waves propagating on type D backgrounds of antinary universe. For a flat transverse space, we effectively deal with Einstein theory. Physical nature can be observed from geodesic deviation of, say, static observers. So we take observers which are not moving in transverse space, take a geodesic deviation equation, take some frame related to the null frame which we had for the discussion of the wild tensor, project this deviation equation for geodesic deviation onto this frame, combine all expressions together, and we can see that there are some longitudinal effects or motion given by the transverse space geometry, and traceless transverse deformations given by psi4 components, exactly what one would expect for gravitational waves. Okay, so this is my summary. We have discussed Kuhn geometries within the Einstein-Gauss-Bonnet gravity. We derived explicit form of the field equations, identified 3 subclasses, discussed geodesic deviation and algebraic structure, and we have also discussed some particular examples as waves in background with constant curvature or Einstein-Gauss-Bonnet PP waves. More details can be found in our paper. So that's all, and thank you for your attention.
Thank you very much, Robert. So I think we have time for one short question, if you have any. Well, if there are no questions, I would like to ask one short question. So there is a point I missed, probably I did not understand. If you go to transparent 13, yeah. So you say there are the 2 cases, D5 and D4. I don't understand the case D4, so probably I missed the meaning.
Yeah. It's not clear from this expression, because you obtain some quadratic equation which you have to solve to obtain exactly this expression for scalar curvature. And
yeah, also you have to divide by 0.
On the level of this equation, you have to separate d = 5 and d = 4.
Yeah, but d is the total number of dimensions.
Yes, exactly.
But in 4 dimensions,
in 4 dimensions, you will obtain exactly GR, because there is no Gauss-Bonnet contribution. And what's interesting, that also in d = 5, in this case, you will effectively deal with the Einstein theory.
Okay. Thank you very much.
You're welcome.
So thank you for this nice talk.
Thank you.
So please stop sharing. So we have now the next speaker, who's Mohammed Sharif. We'll talk about anisotropic solution through decomposing in curvature matter coupling gravity. So please share your screen and go ahead. Yeah. So you should probably unmute yourself. I can't hear you. I don't know if other people can hear you. Hello? Muhammad, I cannot hear you. Is that my problem? Can the other attenders hear
I can't hear.
Okay,
I can't hear it either. And he's unmuted, so.
I think he's not muted. I can't.
No.
Mohammed, do you have some issue with your microphone, I think?
Yeah.
So,
Hello.
Hello. Okay, now I can hear you. So, hello, Mohammed. No, we have no audio. Hello.
Hello.
Yeah, we can hear you now, but I hope it will be. Yeah.
So it's okay. It's okay now.
Now it's okay. Yeah. So please
Okay.
go
Thank you
ahead.
very much. So I'm talking about anisotropic solutions through a particular technique, so-called minimal decoupling technique, in a particular modified gravity, so-called curvature matter coupling gravity. So let me start from the very well-known Einstein field equations. The left-hand side of these field equations are geometric part, and the right-hand side indicates the physical part. So they have been coupled through the coupling constant. Einstein has the belief that this universe is static. So to incorporate these effects, he introduced the cosmological constant. However, later it was removed from the field equations when he found that the Hubble discovery that this universe is expanding. So in 1929, Hubble showed that more distant galaxies were moving away from us more rapidly. So this is the velocity with which the galaxies are moving, and this is the distance, and these are proportional to each other. It is very well known that this universe is composed of this energy budget. It has 71.4% dark energy, which is the maximum part of this universe, and 24% dark matter, and very little, 4.6, is the ordinary matter about which we know. So most part of this universe is unknown. Dark matter is, unlike normal matter, dark matter doesn't interact with the electromagnetic force. So researchers have been able to infer the existence of dark matter only from the gravitational effect it seems to have on visible matter. Its presence is implied in a variety of astrophysical observations, including gravitational effects that cannot be explained by accepted theories of gravity unless more matter is present than can be seen. For this reason, most experts think that dark matter is abundant in this universe and that it has had a strong influence on its structure and evolution. Dark energy is a hypothetical form of energy that exerts a negative pressure, behaving like the opposite of gravity. It has been hypothesized to account for the observational properties of distant types I supernova, which show the universe going through an accelerated period of expansion. Now, there are two well-known issues of this cosmological constant. In fact, there are different ways to explain the expansion of this universe. And in GR, we explain it through the cosmological constant. However, there are two issues. One is the cosmic coincidence problem, that why are the present values of the densities of dark matter and dark energy of the same order of magnitude. And the other one is finite tuning problem. Astronomical observations indicate that the cosmological constant is many orders of magnitude smaller than estimated in modern theories of elementary particles. So when we keeping in view these issues, we try to modify the Einstein-Hilbert action. There are two ways to modify that action. One is to modify the geometric part, and the other one is the matter part. When we modify the geometric part, there are different modified theories. The immediate one is the Frt theory, and next is the coupling of Fr with matter. So I'm going to consider Frt theory. Here R is the Ricci scalar and T is the energy momentum tensor. This theory was introduced by Harco in 2011. In this theory, the Lagrangian is given by an arbitrary function of the Ricci scalar and trace of the energy momentum tensor. This theory allows better understanding of gravitational effects at the quantum level. It can explain transition from matter-dominated phase to late-time acceleration. Now, a few words about compact objects. When we have a low to average mass star, the result of collapse lead to white dwarf. When we have large mass star, we have neutron star, and when we have very large mass star, we have a black hole. White dwarfs are composed mostly of electrodegenerate matter. They are very dense with mass comparable to the sun. They have been detected as sources of lower energy X-rays. Neutron stars are composed almost entirely of neutron degenerate matter. These stellar remnants are extremely dense, weighing millions of tons per cubic centimeter. They are detected from their electromagnetic radiation. Black holes are the most dense objects in the universe. These objects emit no light and therefore don't have a color. Astronomers can detect them by monitoring the behavior of neighboring objects. Now I'm going to discuss the exact solutions through the decoupling technique. This technique can be summarized in these steps. We in fact add a new gravitational source in the original energy momentum tensor. Then we apply geometric deformation on the metric coefficients and split the field equations into two sets. We pick a known solution for the first set corresponding to the original source. The second set is associated with new source. We find a solution of the second set, and then we combine both solutions of both sets to obtain a new solution. So in this way, we find exact solutions. There are two types of decoupling. The first one is the minimal geometric deformation, and the second one is extended geometric deformation. In the minimal geometric deformation is applied only to the radial metric potential, leaving temporal component as an invariant quantity. It works as long as the interaction between the matter sources is purely gravitational. While in extended geometric deformation, it can allow modification in both temporal as well as radial metric functions. The matter sources can be decoupled successfully by allowing the transaction of energy between them. So now we discussed decoupled solutions in this theory. Let me talk some basic formalism in this theory. The action of this theory is given by this expression. Obviously, here Frt is an arbitrary function, Lm is the matter Lagrangian, L theta is in fact the anisotropy, provides it anisotropy, alpha is the coupling parameter. For the sake of simplicity, we take a particular model, which is the linear Frt model. Here chi is the coupling constant of this model. So we can formulate the corresponding field equations in this form, and we consider an isotropic fluid, which is a perfect fluid. Here rho p as the energy density and pressure. We take a static spherically symmetric line element in this form. Here obviously nu and eta are unknown functions of R. The internal configuration of the spherical structure is described by the following matter distribution. This is the total energy momentum tensor. We can say this is the effective, and this is in fact you can say anisotropic fluid. Well, this is the effective terms coming from the theory, and these are given here, and this is due to anisotropy. So we can write down the field equations in this form. Here rho bar and p bar are given here. We know the conservation equations are due to the effective energy momentum tensor can be written like this. Matter parts are given here. This is the total energy density, total radial pressure, and total tangential pressure. And we can define the anisotropy in this way. Now we use extended geometric decoupling technique. In this technique, we in fact modify both radial as well as temporal components. So we consider a perfect fluid solution for the line, this ion element. We applied the extended geometric technique. This means we can modify the radial as well as temporal component. So here alpha is the coupling parameter, H and F are the arbitrary functions which have been added in the original metric functions. Obviously, the first set of the decoupled equations can be obtained when alpha is 0. So when alpha is 0, we in fact go to the original field equations, which are given here without decoupling. And this describes the isotropic configuration. The second set containing evolution equations for the anisotropic source are given here. Okay. The xi mu metric satisfies the Bianchi identity, this one, while the conservation of the extra source leads to this expression. Now we use a known solution, which is the Corkinian or Leakia solution for perfect fluid distribution. In this technique, in fact, we choose a known isotropic solution. So this is the solution where A, C, and D are unknown constants, which can be found through the matching conditions. And we may match the interior static spherical symmetric space-time with the exterior Schwarzschild metric, and these can be found as where D1, D2, D3 are given here. Now to obtain the anisotropic solutions, we take alpha non-zero, because when we take alpha 0, we reach to the isotropic solution. So we take alpha non-zero in the interior spherical object and solve the equations of motion. These equations interlink the 5 unknown functions, namely geometric deformations H and F, source term theta. Since there are 5 unknowns and 3 equations, we need 2 additional constraints to close this system. So we need a constraint. So consider the Mybig constraint on pressure as the first constraint, which is given by. So we choose theta R is equal to P of R. Consequently, the matter variables can be found, which are given here. Constraint 2. In the second constraint, we can apply either a linear equation of state or Bauer's line constraint. So first, we implement a linear equation of state on this in this form. Here, obviously, we take tau equal to 1 and gamma equal to 0 for the sake of simplicity. Along with this constraint, the above equations, the above field equations lead to the following deformation functions H and F. Consequently, we can have the solution deforming metric functions in this form, and this lead to the solution. We can check the physical behavior or graphical analysis of this solution by taking particular values of alpha, chi, and for the star 4U1538 to 52 by taking M this value and R this value for this star. So this is the graphs of deformed metric potentials against the radial coordinate for solution 1. We can see that the metric functions are show an increasing and positive behavior, which is the well-defined behavior for any solution. Further, we can see the behavior of matter variables. Here you can see the energy density in both graphs. We can see the difference of these graphs is we have taken different values of alpha. Here alpha is 0.001, here alpha is 0.003. And similarly, radial and then tangential pressure, we can see that these provide the decreasing behavior uh, uh, but remains in a positive range. So positive domain, it means they are well behaved matter variables. Similarly, the pressure of behavior and tangential pressure behavior. Finally, we can see the anisotropy. It is it, it also provides a positive behavior and have the maximum here. So it starts increasing and then start decreasing, but it remains in a positive range. We
Sorry,
can
you
also
still
check
have
energy conditions.
5
Sorry.
minutes plus, you have
Okay.
5 minutes
Uh,
plus
o-
5 minutes for questions.
okay. Okay. Thank you. Uh, Similarly, one can check the energy conditions for these solutions. These are the energy conditions, mathematical form of these energy conditions. And we can see that from the graphs that these all energy conditions are satisfied because they provide positive behavior as well as zero at zero. So they are all satisfied. We can also check the gravitational redshift. Its formula is given here, and we can calculate mass of the black hole, mass corresponding to this solution. And Buchadal derived an upper bound for the mass to radius ratio, which is given here. And the Ivanov found that the maximum value of the surface redshift for an isotropic compact configuration is given here. And we can check from the graphical behavior that our solution lies in this limit. So it means we have well-defined behavior of mass and compactness factor, as well as surface redshift. We can also check the stability through three ways: causality condition, adiabatic index, and cracking. According to the causality condition, the speed of sound must be less than 1. And according to the cracking, the difference of these tangential and radial pressure is lies between 0 and 1. And according to the adiabatic index, it must be greater than 4/3. This is the formula. So, and we can check from the graphs that they all satisfy, our solution satisfy all these conditions. Our solution is in fact stable. Now we can calculate the second solution by using this the condition, and Cosenza evaluated anisotropic solutions from known isotropic solutions by assuming the energy density of a perfect fluid. This is given here, and we can use this constraint to calculate the solution. And here are the deformation functions. And again, we can see the graphical behavior. We can see that they again provide positive behavior, positive increasing, and battery variables provide obviously decreasing, but remains positive range. And we can see that energy conditions are satisfied. And this the second solution also satisfy the stability conditions, that causality condition, and the limit of gravitational redshift, severely adiabatic index. So with all these means, we can say that our solution is viable as well as stable. So I can conclude my talk that we have in fact constructed anisotropic solutions by using metric coefficients of the isotropic known solution Korkinka or Orensky solution through the extended geometric decoupling technique in this Frt gravity. We have found that both anisotropic solutions are physically acceptable as they satisfy all the essential stability as well as viable conditions for a particular star candidate. The effective radial and tangential pressure increase while the total energy density decreases in response to an increase in the model parameter chi for both solutions. Higher values of the decoupling parameter imply a decrease in the pressure and density for solutions 1 and 2. Solution 2 remains stable for high values of alpha in contrast to solution 1. We can say that our approach is effective, more effective in generating feasible stellar interiors in this particular gravity. Thank you very much.
Thank
Questions,
you,
please.
Mohammed, for your nice talk and for finishing in time. So are there any questions?
Yeah, I've got a question. That particular star you mentioned, is that a neutron
Yes.
star?
Yes, exactly.
So have you given any thought about how your results might relate to, say, the recent results put out by NISA?
Well, I have not checked that one. I have taken the data of that star and checked the viability as well as stability conditions of this solution.
Okay, yeah, I just thought it would be interesting because they're getting results like 2 neutron stars of, say, the same radius but with very different masses.
Mm-hmm.
And obviously that's something that is a bit of a mystery, and I was just wondering, now that you've modeled that particular star, whether you might apply that to that context.
Yes, thank you.
Any other question?
May I ask a question? George Alexeyev. It seems for me that from the beginning you assumed that the function f of r and t is linear. Is it
Yes.
for all your talk or only for some part of it? Because
Well,
the
this is
conclusions
obviously.
don't mention.
Sorry.
In the conclusions, you don't mention that you deal with the linear function f of rt.
Well,
But
my talk is, yes, I have used linear function for this gravity model.
But the conclusions don't
The conclusion,
show
yes,
this
exactly.
explicitly.
Conclusion, yes, include this. Yeah, this is the conclusion includes this linear function. Yes.
Thank you.
Thank you.
Any other question? Well, so I think we can conclude. Thank you, Mohammed, again for your talk. And we resume in 10 minutes after the break at 8 o'clock.
Thank you very much.
Okay, see you in 10 minutes.
Yeah.
So I saw there is a question in the chat. If anyone wants to discuss, we have a couple of minutes. Otherwise, we'll leave this question for later.
Oh, thanks, Fabio. Yeah, I just I'm not an exact solutions person, but just curious about solutions which just wondering if the community has any particular solutions which are particularly sought after for a physical interpretation. I'm just interested in ones that are seeking a physical interpretation. If anybody wants to chip in anything random.
I mean, any exact solution, you mean, or some specific model, or just in GR?
Yeah, I suppose GR, but anything really. I was just curious if there's sort of
well, I think there are plenty of solutions which
as a matter of fact, I will talk about solutions which are not exactly clear.
Yeah, I think there are plenty of examples.
Which ones would be the most outstanding or most sought after, do you think?
I mean, solutions with negative curvature, for instance.
Yeah.
I mean, incidentally, I will talk shortly about one solution, which is a vacuum solution with an hyperbolic foliation, and which is, I mean, you could call it the pseudo-spherical solution. So it's kind of the opposite of the Schwarzschild solution. And you may wonder whether any solution as GR is a gravitational field. Because in that case, you have exactly the opposite situation you find in Schwarzschild, which is you have an horizon, and it is beyond that horizon that you have a dark sector, if you may say so.
Sure. Thank you. I look forward to it.
Okay.
Yeah, I think we are almost ready to start.
I suppose it's me, is it?
Yes, let's wait a few seconds more. So
yeah. So I share my screen, is that so?
Yeah, please share your screen. Share your screen.
Let's see if I can find it. Where is it? The sharing. Just a moment. Okay. It's not sharing yet, is it? No.
No.
No, not now. No. Let me see. Just a moment. This one.
Yeah.
Okay, let me just.
You are page 7.
I'm sorry, it's not this one I want. I'm sorry. Well, I could be, but this is not a good one because this is the latex stuff. Just
yeah,
I'm
use
sorry.
PDF.
Yeah. Yes, yeah, that's what I'm going to do. So, okay, let me just be back. Stop sharing. Is it? No, you're not. Let me just share again. Okay, this is, I suppose. Yeah, I think so. Yeah. So view slideshow.
Yeah, you're page 17.
Too many pages. Sorry.
No worry.
So
okay, so let me introduce the next speaker, who's Prof. José Pedro Mimoso from University of Lisbon. We'll talk about Tolman-Oppenheimer-Volkoff conditions beyond spherical symmetry. So please go ahead.
So good morning to everybody. I suppose it's good morning for many of you, but probably good afternoon or good night for some of the others. I will talk about a work I've been doing in collaboration with Alain Maciel from Brazil and Morgan Ledelieu, who is in Lanzhou, China, although he's now in Paris because he left in 2019 for Christmas and never returned to China afterwards. So the purpose of this work is, let me also, okay. So is to try to generalize the well-known Tolman-Oppenheimer-Volkoff equation, which is here depicted in a way. Sorry, something not going well. Sorry.
You have to,
yeah,
to stop this.
Yeah, it's.
You have to pause here. Yeah, there. Yeah, okay.
Okay, this one. So the idea is to generalize the well-known Tolman-Oppenheimer-Volkoff equation, which establishes the hydrostatic equilibrium of stars, for instance, towards encompassing models with other symmetries, open models in general, with hyperbolic or planar symmetry. This is a well-known equation, the Tolman-Oppenheimer-Volkoff equation. It dates from the 30s. People realized that there was an extension of the classical hydrodynamic equilibrium, which in GR stands like it is written in equation 1, where you have a gradient, a negative gradient for the pressure to sustain gravitational collapse. And the main difference is with regard to the classical continuum mechanics equation is that now we have a rho plus p in terms of the relativistic inertia. So it's the relativistic density of mass in effectively working as an inertia. And we have to account for the curvature, which is given by the 1 over 1 minus 2 gm over r. So this mass here is the usual, it's a counterpart of the classical mass of a star up to a given radius, which is called the Misner-Sharp mass, or Misner-Sharp mass in general, but now also called Misner-Sharp-Hernandez gravitational mass. I mean, this is a textbook equation. It has numerous applications in dealing with astrophysics, astrophysical objects like black holes and white dwarfs and neutron stars is known. I mean, this is a well-known book, and you can find many papers dealing with different aspects of this equation, but mostly all of them looking at situations where you have either a spherical distribution of matter or bound system, or some kind of elliptic distribution, or whatever. So you find many of these books, these works. So what we did was to consider a general class of models which contain the spherical models, but which also extend to planar and hyperbolic models. So it's a warped metric where you have a foliation of the space-time by two surfaces, which may be closed, spherical, planar, or hyperbolic. And we, in our formalism, we've applied dual null formalism in the A-word fashion, although you can do it without, it's not indispensable, in fact, to do this. But so we have a space-time where we can distinguish two orthogonal subspaces, one which is perpendicular to the leaves of these space of this foliation of with the subspaces of constant curvature, and we have obviously the subspace generated by the orbits of theta and phi, which are just coordinates here, not necessarily the angles. We also have an orthogonal two-dimensional basis on the orthogonal space to the leaves with an induced metric. So we can also split the metric into a combination of the metric given by the leaves, which is rescaled by a factor y, times the metric induced on the orthogonal space 2x. So this is basically a well-known formalism. We define null vectors and then we normalize them, and the metric can be written like this. So it's another way of splitting the metric. And we define null expansions in this way. So basically, we have for a vector k, the null expansion associated with this vector is basically this contraction of k with the form of y, which is the factor which scales the subspace, the two-dimensional subspace special of the leaves. And we have, in fact, this is basically a mean curvature, the y over y. And so for any vector, we can define a corresponding expansion in this way. The Einstein equations in this formalism read like this. I mean, this is a bit geometrical. We use the lead derivative along the flow k of the null vector k or null vector L. And we also have a constraint equation here. And these quantities are in affinities. In practice, going back to more traditional splitting with the orthogonal vector, time-like orthogonal vector to the leaves, and the vector n, and we can define the acceleration in this way. And we have also another scalar, beta, which gives the way the normal n evolves along the direction E and on this three-dimensional spatial hypersurfaces. In fact, this vector EA is basically, in this case, the vector along, for instance, in spherical symmetry, along the radial direction. So it's also in the subspace n perpendicular to the leaves. Now, there is a nice result one can find, and it's not surprising. When we have this splitting in the space-time in plus two dimensions, warped, we realize that if there is a killing vector orthogonal to the maximally symmetric hypersurfaces, then the expansion of this vector is vanishing, and this means that obviously the surfaces are of constant curvature. So there is nothing really surprising. But then we want to look at the Tolman-Oppenheimer-Volkoff equation, which involves a mass, which is the gravitational mass in the usual sense. And so we have to, if we are dealing or aiming at describing open or hyperbolic geometries in particular, we have leaves which have infinite dimension, and so it's difficult. They do not form compact closed surfaces to encompass a domain where we integrate and have the mass like we do in general in spherical symmetry. So the problem, and this is basically the central result of this work, the problem is to try to generalize the Misner-Sharp mass into a parameter which can be its extension for the open cases. It is more convenient than to use the Misner-Sharp mass to use the Hawking-Hayward mass energy, which is defined this way. In fact, it involves also the shear and the vorticity, but in this case, we are dealing with, we have null expansion of the two-dimensional hypersurface of the leaves. So we just have to deal, we don't have shear nor vorticity, and so the Hawking-Hayward mass energy reduces to this form. And this is the curvature, the two-dimensional curvature of the leaves, which depends in this case on a parameter epsilon, which discriminates between the different curvatures. And we realize that this second term, which is this product of the the null expansions, in fact, is basically 2 over y squared times the square of the form dy. So if we replace R with this and the product, the normalized product of these 2 expansions by this expression, we get a result which generalized something which is very familiar when we deal with Misner-Sharp mass energy in spherical symmetric objects, which is we have the square of this form is epsilon minus k parameter mu of y, which will represent a generalized mass, and which I will discuss in a moment. And so this is the generalization of this very well-known formula. This is known since basically since Tolman actually, who used these in terms of the gradients of the radial area. So we want to encompass or to look at the open models. And so the trick that we are going to use, technically, I can show you this image here, which is probably more illuminating, which is, since we are dealing with leaves which have, for instance, hyperbolic foliation or form, what we are going to do is we are considering closed volumes where we defined by the foliation and the circles on top of these, like caps, like cylinders, like that. And so what we realized is that we can define a mass using even the Hawking-Hayward mass energy for these conveniently closed surfaces, whereby this mass, the limit when we make the surface extend to infinity, the limit of the mass over the area becomes well defined and depends on y, on the warp factor y. So basically, what we are defining here is for open models, we define the mass, a mass parameter, such that it's a mass defined on the surfaces of the leaves for a given y, which in a way, in this case, could be just the radial, in cylindrical coordinates, the radial parameter defining the throat of this hyperbole. And what we define is this mass parameter over the area. So it's a mass per unit area, is constant over the leaves. This was well known. It's kind of a generalization of what you do in electromagnetic field theory. And it works because now we have a mass parameter which is well defined for open systems. And so we now have a meaning for this mu, which enters this formula here, which analyzes the formula which for spherical symmetry, and we can apply this to equations and to a derivation of the Tolman-Oppenheimer-Volkoff equation. So now we consider a stress energy tensor of this form. Just, I mean, for simplicity, you consider perfect fluid. In this the composition that we are considering, it can be written this way. So when we look at the conservation of the energy momentum tensor and project it on the along E, we get the acceleration. And so the acceleration is given by this, and then using the result that we had proven, which basically states that we are considering leaves of constant curvature, we are able to transform this into a similar equation whereby the area times the expansion along E is given by this, and so we derive a unified Thoma-Oppenheimer-Volkoff equation, which has exactly the same form as before, but now there are two essential ingredients which are new and which include in the open foliations, which is we have a mass which is now defined to also encompass the open foliations, and we have a different expression here, which involves the discriminator for the curvature of the foliations, and so this accounts for the curvature in the general Thoma-Oppenheimer-Volkoff equation. So this is a general equation for open models, and obviously we can also.
Jose, you have 10 minutes, including
okay,
questions.
It's fine. So I have this. We can also introduce an energy density now in a similar way as we do for the spherical models, but there is something which I should have referred before, and which is quite important, which is when we get this equation, which is here 24, we realized that for the open models, we require a negative mass parameter mu. So this is also new. So we have something which tells us that for the open models, this mass parameter must violate the weak energy condition. And thus rho, which is defined by this equation, which is the generalization of the usual equation, now has a negative value as well. So to illustrate our results, we considered a metric of this form, which in particular encompasses or includes the vacuum metric with the hyperbolic foliations, which were discussed by Kunt and Ehlers in the end of the 50s or beginning of 60s. So we can consider vacuum solutions also, but the fact is that when we apply this metric and consider the Euler equation, we have one equation here. We are considering the simplest case just for illustration purposes. So the Euler equation, we will consider that we have a constant density, like in textbooks for first interior Schwarzschild solutions, and we integrate the Euler equation to get this expression of alpha in terms of the energy density, constant energy density, and the pressure. The mass parameter yields this simple expression which generalizes the spherical one, although for the open models rho is negative. And introducing these results into the Thoma-Oppenheimer-Volkoff equation, we get the pressure in terms of the warp factor y, which has this form where yj is the analog of the radius of the object, and ys is the analog of the Schwarzschild radius. So alpha is as this form, and we see that this is a generalization of the interior solutions, Schwarzschild solutions with constant energy density, with obviously the difference that epsilon here is negative, and that these quantities are not really well defined, especially the y's for the cases where we have a negative. So if rho is negative and y is positive, we will have a negative Schwarzschild radius, and conversely, if this is negative. So so we have strange solutions, although they all fit within the same framework now unified. Obviously, what we realize is that for the hyperbolic case, which is the epsilon -1, we have a pressure which now, to satisfy the Thoma-Oppenheimer-Volkoff equation, the pressure now has a positive gradient instead of a negative gradient, and it is only positive beyond a given radius, whereas which is the limit radius of the object in static equilibrium, whereas for the flat or spherically symmetric, I mean the closed model, we have the normal negative profile for the energy, for the pressure, and we have, or for the pressure versus models of the energy density, and the pressures are positive inside the object, obviously. So these are our conclusions. We managed to generalize the Thoma-Oppenheimer-Volkoff to encompass open foliations of the space-time. So this covers models with negative curvature. The price that we realize one has to pay is that we violate the energy conditions, namely the weak energy conditions. And so we have objects which, although are bizarre, they are not too different from objects that one finds when studying wormholes. And if we had considered the killing not to be orthogonal to the leaves, but to be tangent and spatial, we would realize that then we would have Bianchi models, and the corresponding equation, which would generalize the Thoma-Oppenheimer-Volkoff equation, would be also a violation of the weak and strong energy condition, and we would only have the extension of the Thoma-Oppenheimer-Volkoff equation for the killing models, the models with killing parallel to the leaves. Only that would only be accomplished by a cosmological constant. So we realize this means inflation, and so it's not yet again, it's not so bizarre nowadays that we are trying to explain why the universe expands in an accelerated way. Well, this is also, thank you very much for listening.
Thank you very much, Joseph, for your nice talk. So I wonder if there is some question from the audience. Colin, maybe you want to ask a question?
No, I'm fine, thanks.
Okay. So
I stop sharing.
Yeah, if there are no questions, we can go ahead with the next speaker. Thank you very much again.
You're welcome. You're welcome.
Yeah. So the next speaker is Maciej Ossowski from University of Warsaw. We'll talk about non-singular spacetime with the NUT parameter. So please share your screen and go ahead.
Okay, hello. Can you see my screen well?
Not yet.
Not yet.
No.
Maybe now.
Yes. So yeah, now it's okay. So please go ahead.
Okay. So hello to everyone. Thank you for the opportunity to speak here. And I want to talk about my work in collaboration with Professor Jerzy Lewandowski, also from the University of Warsaw. And I wish to talk to you about some singular and geometric aspects of the spacetimes with the NUT parameter. So at the beginning, I should probably say that all of those spacetime, this whole family that I will be talking about, is lambda vacuum, and necessarily in 4 dimensions, and they are all of Petrov type D. So let me focus for a moment on a most basic spacetime with a NUT parameter. So this is the tau NUT spacetime. And actually, this metric might look a little bit familiar. And of course, this is because Newman, Unti, and Tamburino discovered this metric as an extension to the Schwarzschild solution. And so, as is the case with Schwarzschild, we have we have this function f, which is of different form because we have now introduced some knot parameter. We have some horizons which are located at the roots of this function, and we even have for independent Killing vector fields, the same as in the Schwarzschild case. But there's one glaring difference, which is of course the presence of this 2L cosine theta d phi term. And this is the source, this is one of the sources of the singularity when we talk about spacetime with knot parameter. So the form d phi is actually not well defined on the poles. So when we tend to the theta equal to 0 or pi, and we have to multiply it by something sufficiently fast vanishing. And of course, the cosine theta doesn't vanish at all. So a priori, this term is ill-defined. So we have poles which are not regular, but maybe maybe we can gain something by introducing knot parameter, and we can see that there's some benefit. So namely, the surface of R equal to 0 now is not singular, contrary to the Schwarzschild spacetime. So if you look at this function f and plug R equal to 0, we get that it has a finite value. So this doesn't vanish, and also 1 over f doesn't blow up. So we somehow eluded the curvature singularity at the 0, and also as a benefit when consider the determinant of this angular part of the metric. So it doesn't vanish as we tend to the origin, so the spheres do not degenerate because the radius has this additional term of L squared. So if you could somehow interpret away those singular axes of rotation, then the tau knot would be something very nice. It would be a smooth regularizer of Schwarzschild, which also happens to solve Einstein Equations, which is also an exact solution. And of course, there were many attempts to tackle this problem. One of them was introducing some cosmic string along the z-axis, the axis of symmetry, by Bonner, and his observation was that this term, this additional one form with d phi produces a cross term with time, and it can be interpreted as a rotation. So it would be a source of a angular momentum. But for our purposes, the most important interpretation is the one of the Misner. And he, on the contrary, noticed something different, that this rotation has only a local character, and globally we can do something else by imposing certain different topology on our spacetime. So what he did was that he devised some new coordinates, and in those coordinates, our metric tensor, actually 2 copies of our metric tensor, takes this very similar form, but with the difference that there's a cosine -1, which is 0 at theta equal to 0, and cosine +1, which is 0 at theta equal to pi. So in those coordinates, those half axes are actually well and non-singular. Yes, and his crucial idea was to take 1/2 of the left metric, so non-singular at the northern hemisphere, 1/2 which is non-singular at the southern hemisphere, and combine the non-singular patches into one totally non-singular spacetime. And this is perfectly fine, except that now we have to take care of our time coordinate. because it has to satisfy this transformation condition, which simply transforms the coordinates from the one covering the northern part to the one covering the southern part. And now, because the phi coordinate is periodic, we also want the time coordinate to be periodic. So this is a price we pay, which is that in the certain regions of spacetime, we necessarily introduce closed time-like curves. But of course, those regions are not ubiquitous, and we can find some regions of the spacetime where the vector d over t changes its character from time-like to space-like, and the same happens to the vector field d over dr. It changes from space-like to time-like, and this happens precisely in the region between horizons. So this was actually the first place that the tau-NAT metric was discovered by Taub. So he considered it to be a homogeneous cosmological model of Bianchi type 9, and because we are in the region between horizons, this model has this nice feature that it actually doesn't start or end with a curvature singularity. And all of those constructions, I mentioned them before, they will come up in a minute in a slightly different and more extended context. So let me talk about tau-NAT in yet another way. So we can now impose on this spacetime by carefully decomposing the metric tensor in a certain way. We can impose on the spacetime the structure of a U1 principal bundle. So what we have here in red is a connection 1 form of this principal bundle, and in the red we have the metric on the orbit space, or if we talk about principal bundle, this would be metric on a base space. And what we also need is a generator of this U1 action, and it will be in Killing vector field d over dt, which now generates the U1 action because we made the time periodic. So another feature is that when talking about this way, about tau-NAT spacetime, we see that what we have actually done is to compactify the orbits of this Killing vector field from a real line to simply some circle. And the resulting spacetime in this form can be interpreted as a U1 principal bundle over R times S2, which is now R times S3. So taking advantage of this fact that T is now periodic, we incorporated it in a S3 structure, three-dimensional sphere simply. So to make this point even further, we can actually introduce left invariant Killing vector fields and dual with left invariant 1 forms, and write the metric purely in terms of those left invariant 1 forms, also with some dr term here. Okay, so that's the historic part of the talk. Let me now show you some of our results. So we are focusing on adding to this spacetime more parameters, and the natural extension is to add the Kerr rotation parameter and also some cosmological constant, resulting in a Kerr-NAT anti-de Sitter spacetime. So let me talk about some features of this metric. The overall form should be familiar because those are like Boyer-Lindquist coordinates, and again, the vanishing of function sigma gives us the here a Kerr ring-like singularity. So if RL would be equal to 0, this would be precisely the term generating this ring singularity. But now we have this additional feature, which is also something, well, what we saw in the tau nut case, that if we choose sufficiently large nut parameter, this ring-like singularity is completely non-existent. It's completely avoidable. So again, we have this behavior of regularizing some well-known black hole solution. We have some formal conditions like P has to be equal than greater than 0 to maintain the Lorentzian signature. And also we find here the term that was problematic in the tau nut case. So this one form now is A d phi. And while sine squared theta is completely fine, sine squared of half over theta is again singular, but now we have started with the coordinates that are non-singular only in half of the axis.
Sorry, you have still
but again
10 minutes, including questions.
Thank you. Also, we have up to 4 Killing horizons defined by the roots of this polynomial generated by 2 Killing vector fields. So again, we wish to impose some U1 pre-simple bundle structure. Again, we're looking for a bundle of R times S3 over R times S2. So we'll need some generator of this U1 action. We'll look for some connection, some lapse function, and of course the metric on the space of the orbits. And the overall form is actually very similar to what we've seen in the tau nut case. So let me jump to the first example, first attempt of our solution. So if you would simply take dt as a generator of this action, our decomposition would look something like this. And here we can see that there's a new type of problem which was not encountered before, namely that we have a canonical singularity on the S2 part of our base space. So now this angular part of the metric has canonical singularity. As our second attempt, we try to do something smarter. So maybe you have to change the generator of our U1 action. And to do that, we consider a general Killing vector field. And because we are only interested actually in the orbits of this field, it's sufficient to consider one-dimensional family parameterized by B, which gives us everything except the pure rotation. So we can introduce some adopted Killing coordinates in which the Killing vector psi is simply d over d tau, and our coordinates a priori leave our angular coordinate a priori lives in some interval which is yet to be discovered. So the method of removing the canonical singularity is quite standard. We require that circumference to the radius has to have limit to pi as we tend to the poles, and we devise this continuity condition. This condition is quite a convenient one because it's R independent. So it means that if we can remove this canonical singularity at one of the spheres, the same condition works for all of the spheres. And we do that by appropriately rescaling the coordinates such that it lives in a 1 to 2 pi interval, as it should be. Okay, so let me talk a little bit about this continuity condition. So some features of it, some special cases. When R is equal to 0, so we have no nut parameter, this condition is trivially solved because P reduces to 1, and here in the denominator we also have 1. And this is probably the reason why we usually, when dealing with black hole solutions, we don't really have those problems. We don't encounter those problems because all of the Killing vectors are fine and they generate non-singular geometry. And of course, precisely in those cases, we don't need to do any gluing. If L is equal to 0, but either A or lambda are 0, then we can, as in the tau-NAT case, perform the gluing using the d over dt Killing vector. And in generic space, we have two principal Killing vector fields, as we call them. But luckily, they are equivalent in the sense that they generate the same geometry. And so we have two solutions to these conditions, two because of this absolute value. And what we basically have is that for any choice of parameters, we can plug it in and read off an appropriate Killing vector, which we can use to glue the spacetime. So there are some things that we also have to take care of. It would be nice to have some way of knowing what's the transformation between the patch that covers non-singular patch that covers the northern hemisphere and the southern hemisphere. And we do that also motivated by the tau-NAT example. So we look at the phi part of the connection one form and discover that it's of course well defined in one of the poles, but has some constant value in the other. And because it's a constant, so it's R independent, we can read off the transformation for all of the spheres simultaneously and introduce the coordinate transformation, which precisely removes this obstruction. So I've been talking about the continuity condition, and this is because the smoothness actually has to be checked by hand, which we have done, and we're in luck because our solutions are not only continuous, as would the geometry suggest, but also smooth. So there are also some applications to horizons, and for that we introduced the notion of projective non-singularity for the horizon. So this is when not only the horizon as a free manifold is non-singular, which is always true in our approach, but also when the geometry of non-singular spacetime agrees with the geometry of the horizon. So this happens precisely when the space of null generators is non-singular, and when we take the base space of our principal bundle to be the space of null generators. So then we have to necessarily use the Killing vector field that develops the horizon. And as it happens, it's only valid for the de Sitter spacetime, as we necessarily cover that lambda has to be greater than 0. At most, one of the horizons is non-singular because we have to, by hand, put this r equal r0, which is the radius of the horizon term. Also, either outer or outermost or innermost horizons can be non-singular, and they're also non-extremal. Another application which we can immediately get is that we can look for such parameters that we would get this cosmological behavior where there are no closed timeline curves, and this happens if the Q function, which governs the roots of the horizons, is lower, it's smaller than 0, and in this case also we have no horizons. So we can look at this solution as a cosmological solution, but now we are not constrained by the horizon, and the whole spacetime can be regarded as this cosmological model, which is inhomogeneous, has no and has no singularities whatsoever. And well, maybe I won't talk about the global structure because it's all derivative of what I said, but we can have some nice pictures to represent it. I would rather briefly mention that the same procedure can be applied to the most general vacuum, lambda vacuum type D solution, which are a subfamily of Plebański-Demiański family of solutions in this form devised by Podolsky. So this metric is very similar in form, only we have much more complicated functions. And it also turns out that this conformal factor doesn't impose any additional conditions. So we actually recover that most of the things that I've been talking about can be performed for this metric. It would be only more cumbersome to start with it as an example point. But all of the things I've been talking, so the bundle structure, gluing, equivalence can be achieved for this metric. There's also one additional thing that for the simply accelerating spacetime, so with no L, it's not possible to get rid of the canonical singularity. But somehow, if we include the knot parameter, we can do it. So that's something that wasn't possible without the knot parameter. Okay, so that's all from me. Thank you for your attention. I hope that I convinced you that introducing knot parameter to our standard black hole solutions gives us some trouble, but also solve some other problems that we normally have. Thank you.
Thank you for your talk. It was nice. So, questions from the audience? No? So if there are no questions, I will suggest to go ahead with the next speaker since we are on time. So the next speaker is Daniele Gregoris from Jiangsu University of Science and Technology. So Daniele, please try to share your screen, and if it does not work, I will share your transparencies.
Okay, good morning. Can you hear me?
Yes.
Perfect. And can you see my screen as well?
Yes. So please go ahead.
Okay, so the title of my talk is Thermodynamics of Shearing Massless Scalar Field Spacetimes is inconsistent with the wild curvature hypothesis, which is a project I have performed together with Yan Qinong and Bing Wang. This project relies on the spacetime metric I am reporting here. You can see that it describes a spherically symmetric, inhomogeneous expanding universe. And this metric comes with both, with either closed and open topologies according to the value of this parameter epsilon. The metric is based on three free parameters, which are A, B, and C. And also we have this function h of t, which is a sort of scale factor. You can also see that only the angular part of this metric and not the radial one is time expanding. This metric is an exact solution of the Einstein field equations of general relativity. And it is supported by a perfect fluid governed by this equation of state. So you can see that if we killed this term by setting C equal to 0, we would have a stiff matter fluid, which is equivalent, as we know, to a massless scalar field. Also, this constant C can be regarded as a bug energy if we adopt a language from particle physics theory. In fact, when the energy density rho is 0, the pressure may be not vanishing thanks to this constant C. In general, we can recast this equation of state as an effective energy-dependent equation of state parameter multiplied by the energy density. So here we have what has been called a chameleon field. This space-time metric is not a model that we have cooked up for achieving our purposes, but indeed has been found and studied by several authors many years ago. So let me now report some basic information about this space-time metric. I am writing down the energy density, and in particular we see that we have this piece at its denominator. So when this quantity will be 0, the energy density will diverge, and this will be the Big Bang time. Also, I would like to mention, as it will become handy later, that if we choose epsilon equal to 1 as a topology, and this scale factor with A and B positive, clearly this model will come without a Big Bang singularity. Then a meaningful cosmological application would require the energy density to stay positive all along the time evolution. And so this naive requirement would set a constraint on the constant C, which is the bug energy of the model, and some constraint as well on the quantities A and B. Then we can compute easily, or find in some literature paper, the Hubble function, and you can see why I have said that this factor h of t is a sort of a scale factor, and you can also see that a positive time derivative would imply an expanding universe. We can compute the invariant shear, the matter parameter, the deceleration parameter, and also psi2, which is the Weyl scalar from the Newman-Penrose formalism. So let's now start to put some physics into this space-time metric. And I would like to investigate its thermodynamical properties. So I would like to study the cosmological holographic principle as formulated by Bosso, according to which the entropy of a physical cosmology should be bounded above by the horizon line. Also, we have the second law. So I would like to understand if the entropy related to the matter content is an increasing function of time. So we can expect that these two conditions may rule out the model, or may be trivially satisfied, or as it will actually happen, they would set some constraint on the cosmological parameters A, B, and C, and so, for example, on the matter density. So let's now move to some more technical aspects. So for studying the cosmological holographic principle, I go back to the metric and I find the RL radius. Then I search for the location of the dynamical apparent horizon, and I impose that the gradient of the RL radius, the norm of this gradient, should vanish. I get an algebraic equation, and it can be seen that we will have a non-complex solution for R only for the closed topology, epsilon equal to 1, and when the constant C is negative. In such a case, we find the location of the dynamical apparent horizon. This value is well defined clearly if the argument inside the square root is positive. So we get a further constraint on the values of A and B, which imply the following physical result. We get automatically, from imposing the cosmological holographic principle, that the deceleration parameter is negative. And automatically we get that the existence of a dynamical apparent horizon would imply that this model comes without Big Bang singularity. Then we compute the area of a region bounded by the dynamical apparent horizon, and we compute the entropy of a matter content inside this region. So this alpha tilde is a constant inside which I put some factors pi, h bar, k Boltzmann, and so on. And this quantity is scaling as the cube of R. We impose the holographic principle, so the matter entropy over the area of a dynamical apparent horizon should be bounded by 1/4 in natural units. And you can see that in the case of a black hole, you will get the Hawking-Bekenstein entropy. So this is why we have a factor 1/4 here. We work out some appropriate algebra, and again we get another constraint on the value of C. Then let's go to the second law of thermodynamics. We require the matter entropy to be an increasing function of time. So by looking at this expression in terms of R of the dynamical apparent horizon, this R must be an increasing function of time. We work out the appropriate algebra, and we get the second law of thermodynamics imposes a lower limit on the size of the universe, or equivalently on its edge. And also we get that the Weyl curvature, as quantified by the Newman-Penrose scalar psi2, is decreasing in time. So the first message of my talk is that we can impose these two theoretical requirements and get some and extract some physical meaningful information on the cosmological model we have in hand. Let's now move to the second part. So far, I have considered only the entropy of a matter field. However, there is also the gravitational entropy, which is related to the free gravitational field. Entropy, as we know from many textbooks, is a measure of the disorder within the system. So, which means that as some astrophysical structures is forming inside our space-time, the gravitational entropy should increase because the space-time is becoming more inhomogeneous. Because in one region, we may have an astrophysical structures, and in another one, we may have instead something empty. And so if we wanted to investigate whether other cosmological model is useful for describing the structure formation problem, we need to quantify this gravitational entropy. So how to compute it? We have followed a formalism proposed by Clifton, Ellis, and Tavakol. Indeed, this formalism has been already studied by several authors for describing the formation of astrophysical structures, galaxies, filaments, voids, and overdensities in late time cosmology. So they have assumed dust, and they have used both exact and approximate formalism. Our fluid, as I said, is different, and so we will discuss at the end a possible appropriate astrophysical application. This formalism for computing the gravitational entropy comes with many desirable features because it has been shown that it quantifies the local anisotropies of the gravitational field. It is consistent with the Bekenstein-Hawking entropy of a black hole, and it increases during the structure formation phase. And also, it is at zero in and only in conformally flat spacetimes. So, for example, this gravitational entropy will be zero in Friedmann, which is homogeneous and isotropic, and indeed in Friedmann there is no structure formation. So this formalism is based on the null frame that we use in the Newman-Penrose formalism. We compute, and also here we see that the density of the gravitational entropy depends on the shear tensor, on the energy density and pressure of a cosmic fluid, and on the electric wave tensor. So we have an exact solution in our hand. We apply this formalism and we get a nice formula. So let's see now what is the physics beyond this formula. So here I am plotting the time evolution of a space-time shear, and which quantifies the evolution of spatial anisotropies within the model. And in these 6 figures, the numerical values of A, B, and C have been chosen as to satisfy the cosmological holographic principle and the second law of thermodynamics for the matter. Then I am plotting the time evolution of a wide curvature, which physically essentially means the evolution of the strength of tidal forces. Finally, I am plotting the time evolution of the time derivative of the density of gravitational entropy. So we can see that in these last figures, this quantity is positive. So this is a first derivative, and this means that the gravitational entropy is an increasing function over time in this model. And so it means that structures are formed. And in fact, we can see that indeed spatial anisotropies are increasing, which will mean that if we look in one direction, we may see an astrophysical structures. If we look in another one, we may not see it. So this is the meaning of anisotropy. We see, however, that the wide curvature is decreasing in time. And indeed, our gravitational entropy is increasing thanks to the increase in the space-time shear. So this challenges somehow the wild conjecture formulated by Roger Penrose, according to which the wild curvature is a good measure for quantifying gravitational entropy. Because indeed, we see that the relationship between gravitational entropy and wild curvature is slightly more complicated than that. So let me conclude by discussing some intuitive astrophysical applications of our research. So usually the structure formation problem in the standard model of cosmology is tackled by studying perturbation techniques over homogeneous and isotropic Riemann numbers. However, there are some astrophysical structures which cannot be accounted by such a formalism. In fact, there is astrophysical evidences that in our universe there are the large quasar groups whose sizes are about 70 and 300 the homogeneity scale of 150 megaparsec assumed in standard cosmology. Also, there is evidence of a huge quasar group with a size of 500 megaparsec, which should have formed at a redshift 1.27. Perturbation techniques cannot account for the existence of such structures because applying general relativity there would be not enough time for having such matter collapse. But this is important because they are the seeds for the cosmic filaments and worlds. So our proposal is that an inhomogeneous space-time metric can indeed tame this problem. And in particular, since our model comes with some non-standard, some strong evolution of a shear, and it comes with a stiffened fluid, we believe that this space-time metric that we have found in the literature may have some good and useful properties for describing the formation of primordial astrophysical structures. And that's all about my talk.
Thank you very much, Daniele. So, questions? Okay, if there are no questions, I will conclude. So, well, I would like to thank all the attenders and all the speakers of these sessions. Even if there is some questions, some general questions you want to discuss, we can take some minutes to discuss further. If not, I will just thank you so much for attending this session, and thanks also to Susan Scott and Georgia Alexeyev for co-chairing these sessions. And so if there are no other questions or discussions, I will end the session now. George, Susan? Do you have something to add?
Yeah, just to thank you as well. It's been very entertaining, both the sessions. So thank you to you as well.
Yeah, thank you very much. So have a good day, everybody, and see you again.
You too. Thanks for organizing.
Bye.
Goodbye.
Bye. Bye.
Bye. Bye.
Bye.
Bye. Thank you.
Bye. Bye.